The James Webb Space Telescope successfully launched on December 25, 2021 and is now on its way to its future site at a distance of 1.5 million kilometers from Earth. All astronomers rejoice at the successful launch and anticipate outstanding research results that should greatly expand, if not change, our knowledge of the universe. So why is it so important for science, and what achievements can we expect from this result of years of work by the Webb developers? The James Webb Space Telescope, JWST, has several advantages that other existing or soon-to-be existing ground-based or space-based telescopes cannot match. JWST itself has been a true long time in the making and has been threatened with closure more than once. The project started in 1996 and by the time of launch has cost nearly $10 billion. Such terms and costs are determined by the high complexity of the device and the requirements of the accuracy of construction, quality of observations and 10 years of active life. A distinctive feature of the telescope is its main folding mirror, made up of 18 hexagonal segments. At a telescope, not only the mirror, but also a thermal shield is folded out, and together with optical elements JWST becomes the real space transformer. The new telescope is most often compared to the Hubble Space Telescope, which has served world science for over 30 years. The diameter of the main mirror of the Hubble is 2.4 m, and the JWST is 6.5 m. On Earth there are telescopes of larger size, for example, Big Canary has a diameter of 10.4 m, but because of the atmosphere it can only compare with Hubble, and that not in everything. I will try to list the advantages of JWST, which determine its flagship value for the entire world astronomy for the next decade. Placing the telescope in space has several advantages. First of all, it gets rid of the distorting effects of Earth's atmosphere. At the same time now mastered several methods to improve the quality of observations of Earth telescopes. Some 8-meter Earth telescopes in a number of possibilities already exceed the same Hubble, but the absence of the atmosphere is not the only advantage of space. Space telescopes have the ability to accumulate light for long periods of time during observations. In photography, this is called shutter speed, which is the open shutter time during which light is projected onto a light-sensitive element. And the capabilities of digital image processing make it possible to summarize several frames of the same location. Together, this allows a long accumulation of photons. For example, the record-breaking Hubble Extreme Deep Field captured an image with a cumulative shutter speed of 2 million seconds, or 23 days. This view allowed a glimpse into the early times of the universe to 13.2 billion years ago, meaning that the oldest of the galaxies imaged is about 600 million years old from the Big Bang. The Hubble telescope is located in low Earth orbit, and this is not the most convenient place for such an instrument. The Earth and the Sun interfere with observations, and part of the time eats up the lower radiation belt. But such an orbit gave the opportunity to conduct maintenance of the telescope, which significantly prolonged the time of its operation. The JWST telescope is located more conveniently for observations, but inaccessible to shuttle servicing at the Lagrange point L2 in the Earth-Sun system. This is the region of space from which both the Earth and the Sun are always roughly in the same region of the sky. This means that observations of selected targets won't have to be interrupted every 45 minutes, as is the case with Hubble. JWST will always be oriented with its back to the Sun, which means that the rest of the sky will be available for observations. The annual motion around the Sun allows observation of any point in the universe. Such conditions make this point popular for space telescopes, and the Gaia and Spectrum-RG telescopes are already there, before that Herschel and Planck worked. But we should not be afraid that telescopes there will hit each other's sides. In fact, none of these telescopes will actually be at the L2 point, since it is unstable, and they fly in a wide halo orbit around it. At the same time, the halo orbit can reach 1.5 million kilometers in cross-section, i.e. the collision probability for such telescopes is much less than the danger of meeting space debris in low Earth orbit. JWST is about 2.5 times the diameter of Hubble, and this is one of the important parameters determining the telescope's resolution, i.e. the ability to distinguish the smallest details in the images. However, the resolution of a telescope also depends on the wavelength of light at which the observation is made, and here the infrared telescope loses to one that observes in the shorter visible wavelength range. The wavelength of light visible to our eyes is, on average, 0.5 microns, while the main instrument's JWST register from 0.6 to 5 microns, which means that the resolution of JWST images will start from double the Hubble due to the larger diameter of the main mirror, and go to 5 times less resolution because of the longer wavelength of light. But the telescope's large diameter also means a larger area of the main mirror collecting light. Here JWST is 5 times superior to Hubble, which also increases the quality of observations. Ensuring thermal conditions in space is a complex engineering task that depends on the conditions of the spacecraft. For example, the Hubble telescope's thermal insulation is primarily concerned with keeping the telescope's temperature stable, regardless of its location on the solar or shadow side of Earth orbit. However, the temperature of Hubble itself and its light-sensitive detectors is close to room temperature. In contrast, JWST has an operating temperature of 223 degrees below 0 Celsius. This allows you to observe many more objects in space that emit or reflect light in the infrared. JWST's 5-layer heat shield immerses the telescope's optical systems in an artificial shadow, causing them to cool to ultra-low temperatures through natural radiation. In addition, one of the telescope's instruments has an active cooling system that lowers the detector temperature by another 44 degrees to -267 Celsius, or 6 Kelvin. All this is necessary to see not only farther and deeper but also cooler or darker. Astronomical observations are now made in almost all bands of electromagnetic radiation, but there are 2 main reasons that have made infrared the priority for JWST. These are interstellar absorption and cosmological redshift. The first effect is caused by dust in interstellar space, and the second by the expansion of the universe after the Big Bang. Space is a pretty dusty place. Although we can't see it with our eyes, one of the reasons our sky doesn't shine with billions of stars is because of interstellar dust. Astronomers even have the term avoidance zone, which is the part of the sky where the clouds of interstellar dust in the plane of our galaxy are so dense that they prevent observations of distant objects. It is the interstellar dust that has long prevented the presence of a supermassive black hole in the center of our galaxy from being confirmed, and it is through infrared observation that this has been confirmed. The reason for this advantage of infrared light is simple: dust absorbs light at a wavelength that is shorter than the size of the dust particles. The size of interstellar dust particles ranges from 0.1 m to 100 m, and their number increases in proportion to the decrease in their size. That is, at a wavelength of visible light about 0.5 m, light in interstellar space will be absorbed much more efficiently than in the longer wavelength infrared range. This can be clearly seen when observing the dustiest parts of space. It is possible, of course, to go into even longer wavelengths, sub-millimeter and millimeter, and then the dust will be even less of an obstacle. This way go Russian scientists creating the telescope millimetron, but then there is a growing problem of reducing the resolution of the telescope, which was mentioned above. Thus, the infrared range for JWST is a compromise between being able to see just a little bit into the interstellar clouds, and still keeping the images sharp. Cosmological redshift is another problem with conventional telescopes, which prevents the same Hubble from seeing the most ancient galaxies. Our universe is spreading out in different directions, which leads to a stretching of the wavelength of light from distant sources. This means that the older the cosmological object, the redder it will look. At some point its light will finally leave the visible range of light into the infrared part of the spectrum, and even the mighty Hubble will not see it. That is, JWST is tasked with observing the process of formation of the most ancient galaxies. Today, for example, scientists don't understand how supermassive black holes formed in the centers of galaxies. How ordinary black holes appear, we have already figured out, but with the supermassive still a mystery. It seems to be possible to achieve it by merging of many ordinary black holes, but where to get them in necessary quantity at the early stage of life of the universe? It is still unclear. Except, actually, optical features, James Webb Space Telescope has also a rather serious set of spectrometric instruments, so some of its discoveries will not always be accompanied by beautiful photos. It may also find organic matter in the water fountains of Enceladus and Europa, and determine the composition of the atmospheres of relatively close exoplanets. Perhaps it will be thanks to JWST that an Earth-like planet suitable for resettlement will be found near some of the neighboring stars, in case Earth is in danger of being destroyed by some comet from the Oort cloud. Subscribe to the channel and share this video with your friends. Give it a thumbs up. Tell us interesting facts you know about the topic of this video. See you in new videos.